Hi everyone! In this video we're going to learn how to graph a polynomial function. Here's an example of a graph of a polynomial function. In the previous video we already talked about how a graph of a polynomial function is always smooth, it doesn't have any sharp corners, and continuous. I'm always able to trace the graph of a polynomial function without raising my hand. In the previous video we also learned about the AND behavior of a polynomial function. Well, in this video we're going to learn more facts and features of a graph of a polynomial function that will help us to construct the graph from an equation. Let's talk about important points of a graph of a polynomial function. First, the x-intercepts. The x-intercepts are the points where a graph of a function crosses the x-axis. To find the x-intercepts of a function, we set the function equals 0 and solve the resulting equation. And that's why the x-intercepts, or the values of x at which graph crosses the x-axis, are also called zeros of the function. And of course they're also the same as the real solutions of the equation when we set the function equals 0. Well, that's because that's exactly how we find the x-intercepts algebraically. We'll have more videos dedicated to just zeros of the function. Let's go back to the graph. Another important point on any graph of a polynomial function is the y-intercept. That's where a graph crosses the y-axis. And since y-intercept is always located on the y-axis, the x-coordinate of the point representing the y-intercept is always 0. And we use this fact to find the y-intercept algebraically. So to find the y-intercept, we'll let x be equals 0. In other words, we plug 0 into the function, simplify the expression, and obtain the value at which graph crosses the y-axis. In other words, the y-intercept. Other special points on the graph of a polynomial function are the turning points. Graph changes its direction at the turning point, either from increasing to decreasing direction, or from the decreasing direction to the increasing direction. And here's one interesting fact. If f is a polynomial function of degree n, remember n is the highest power of x in a function, then the graph of the function f has at most n x-intercepts and at most n minus 1 turning points. This is something that we can use as a guideline when we're graphing a polynomial function. For example, function f of x equals negative 2x to the 5th power plus 3x cubed minus x squared plus 7 has, think how many x-intercepts and turning points. Well, it has at most 5 x-intercepts because 5 is the highest power of x. At most 5 means that it can have 5 x-intercepts, 4, 3, or less. Up to 5, in other words. And at most 4 turning points, n minus 1, right? So you take the highest power, subtract 1, and that's the maximum number of the turning points that the graph can have. In the next example, we're going to practice finding the x-intercepts of a graph of a polynomial function. And that's the step that we're going to take. We're going to set the function equals 0 and solve the resulting equation. Here's our first function. To set function equals 0, basically it means that we have to take the right-hand side of this function and set it equal to 0. And now we have to solve the resulting equation. For that, we're going to use what's called the zero product property, which says that if product equals 0, and product is when we multiply expressions or numbers, then it's either the first expression as 0, second, or third. In other words, we set each factor equals 0, and then solve for x. It's x equals 3 for the first one, x equals 4, and then x equals negative 1. So these are the x-intercepts for the graph of the given polynomial function. So graph of this function would cross the x-axis at 3, 4, and negative 1. Notice that these are all real numbers, and only real numbers can be x-intercepts. If it happens that we solve this kind of equation and obtain complex solutions, well, those will not represent x-intercepts. Let's try the next example. To find the x-intercepts for the graph of the given function, again, we set it equal to 0 and solve. This function is given to us in this factored form, which is very convenient because we set each factor equal to 0 and then find x from there. So it's x minus 1 equals 0, or x plus 7 to the 4th power equal to 0. From the first part, we can find that x equals 1. And in order for us to find x in this equation, first we're going to clear the 4th power by taking the 4th root of both sides. fourth root on the left and on the right. Now the fourth root cancels the fourth power, so we have x plus 7 equals 0. And then from here we can see that x is negative 7. So it looks like we found two x-intercepts, x equals 1 and x equals negative 7. But this is what I'd like to note. X plus 7 to the power of 4 is the same as the expression x plus 7 multiplied by itself 4 times, right? That's the meaning of the power 4. Well, it means that if I expand it like that, then I would have to set each factor equal to 0, and I would find that x equals negative 7 4 times. Well, of course, that represents the same x-intercept, x equals negative 7. However, we say that a solution, which is also called a zero of a function, has multiplicity 4. And overall, all such solutions, or in other words, all zeros of a function, would have certain multiplicity. And it's just the number of how many times that solution or zero occurs. So x equals 1 has multiplicity 1, and x equals negative 7 has multiplicity 4. When a polynomial function is given to us in factored form, it's very easy to determine multiplicity by looking at the power of each expression. Notice that we have power 4 here. That's where multiplicity 4 comes from. Here we have power 1, so x equals 1 has multiplicity 1. Multiplicity will play an important role when we start graphing polynomial functions. Well, let's finish our last example. Let's find x-intercepts for the graph of this function. For that, we have to solve the following polynomial equation. Again, it's already in factored form, so we need to set each factor equals 0. Keep in mind that constant factors we don't need to set equal to 0 because 5, well, it's not 0 and it's never going to be. We only use factors involving variables. So it's x plus 3 equals 0 or 4x squared minus 1 equals 0. On the first one, we find that x equals negative 3. That's the first x-intercept, which has a multiplicity 1, right? And to solve this equation, we'll try to get x by itself, since there's only one term involving x. First, I'll add 1 to each side. 4x squared equals 1. Next, I'll divide by 4 on the left and on the right. So x squared equals 1 over 4. And finally, I take square root of each side. Keep in mind that when we solve an equation and have to square root both sides, we always get two solutions at the end. One is always positive and one is always negative. Well, in this case, it's 1/2. Plus and minus 1/2. Well, that's because no matter what I square, 1/2 or negative 1/2, I will go back to the previous step and get 1 over 4. So don't forget about these two signs. Well, and these are two more x-intercepts that we found. So the x-intercepts are negative 3, negative 1/2, and then positive 1/2. And there is one more thing that we need to discuss before we're ready to graph a polynomial function. And these are the three types of the x-intercepts. And they're all shown on this graph. Do you see those three x-intercepts and how different they are? Well, the first x-intercept is right here. It's an x-intercept because this point is on the graph and on the x-axis. As you can see, technically, the graph does not cross the x-axis at this point. It only touches the x-axis. And that's how we're going to call it, the touch point. And this kind of x-intercept occurs when multiplicity of 0 is even. 2, 4, 6, and so on. And when I say 0, I think about a solution to the equation when we set function equals 0. Remember, we just did it in the previous example. Well, here's our next x-intercept, and here it's clear that the graph crosses the x-axis at this point, so we'll call it the cross point. And this type of the x-intercept occurs for zeros with multiplicity 1. It has to be exactly 1. And here's the third x-intercept. It's an interesting one, right? It's called the point of inflection. While the graph crosses the x-axis at this point, we see how it bends. And this is how I like to think about the way the graph bends around this point of inflection. On this side, I think about it as the half of the frown. And then it changes to the half of a smile. And of course, it can be the other way around. Okay, so knowing how to find the x-intercepts and determine the types of x-intercepts, as well as knowing how to find the y-intercept and determine the behavior of the endpoints, all that will be enough for us to sketch a graph of a polynomial function. We're gonna try that in the next video.